Audience, welcome back to Popular Science Lectures. This is going to be the 78th lecture. 79, yeah. 80th is going to be held in Madras Christian College in October 4th. And we will followed by 3 Nobel Prize lectures. And we will also have one more lecture in October, on October 26th. So that's our program. So today it is going to be a different topic. We have the scientific drilling. It's a very interesting thing. How does we reach this? So there was an article in Indo Science. I think people who are having the e-paper alone have the access to the science page of Hindu. So there was an article. It was written by 2 scientists. One is Dr. Sukanta Roy, another one is Dr. Ravichandran. So by reading the name, I thought that he may be living in Chennai. Then I just Google it and find out that he is a secretary to the Ministry of Earth Sciences, and he is reporting to the Ministry of Minister. Just shoot a mail to him on his official address. To my surprise, I get back the reply within a day. So I sent all the profile of Tamil Nadu Science Forum, the list of lectures we had, all these things. He is quite impressed. No, we should do it. I'll support you. And we have the NIOT in Chennai, which is under Ministry of Earth Sciences. And incidentally, Dr. Sukanta Roy, who is the co-author of this article, he used to visit Chennai in NIOT, and you coordinate with Sukanta Roy, and he gave the address. He gave his email ID. So I shot an email ID to him. He responded within a day. That's the beauty. Within a day, and he spoke to me. Now I was not in station, I was in US, and he asked me my mobile number. He called me through WhatsApp call, and we had a long chat. That is how we are here now, and it's a very interesting thing. And he said, no, I want to visit Chennai. I'll inform you 15 days in advance. Whenever I am visiting Chennai, please you make sure you can go ahead and organizing the event. So a couple of weeks back, he called me and said that I'm going to come to Chennai on between September 24th to 26th. Then I chose the midday, 25th. So we have an issue. We don't have any such lecture in weekdays. How are you going to have the weekdays? Now we see that the entire hall is being filled. So we worked with our EC executive committee members, worked together and find out that we'll go to the colleges, with geological department, all these things. Finally, Aditya take a pain of visiting all colleges in and around the area. And most of the HODs of the colleges are very receptive and make the students to attend. Don't miss it. It is a different topic. Please go and attend the lectures. That's how we are here. So let me come back to introducing the Tamil Nadu Science Forum as usual. TNSF is a voluntary organization. It was started in 1980 in the same campus. So one among the founder members, Dr. Murugan, is sitting here, and Dr. TRG, and so many research scholars who are doing PhD, they started Tamil Nadu Science Forum. Initially, it was conducting lectures, hall lectures, only in universities. And it is only confined only to the students. So later part of the 80s, so it was decided to go out of the hall, take the science to the people. So they started developing some kit and go to the streets and have some awareness lectures. All these things were done. And at some point, they decided to go for a science yatra. So we had a science yatra from Kanyakumari to Chennai, covering so many villages and conducting lectures. And the next phase of development, we get involved in the total literacy movement. So we were involved in the Virudhunagar district and Pudukkottai district initially. Later, the entire Tamil Nadu has gone for the literacy movement. It was a functional literacy movement, and TNSF was very much involved in it. We get a lot of volunteers, and the TNSF has expanded throughout the Tamil Nadu. And so we have the district units and branches throughout Tamil Nadu. We had around 60,000 members. And all districts have district bodies. and we periodically conduct conferences, all these things. Our functioning is now divided into 6 different verticals. The first one is the science propagation. We are part of science propagation. We not only focusing on science propagation, we also get into the science publications. We have a separate wing that is working on the science publication, and we have one more wing working on the environment and development. And another interesting thing is now we want to rope in more women in science, for which we have a separate body called Samam, equality. In Tamil it's Samam. Samam is focusing on women in science. So that's how we have so many verticals working on it. I want to make an appeal through this platform. Become a member, all of you, to become a member of Science Forum. You have a lot of places to work on it. We have whatever the area you are interested in, you can find it inside. Some people are very much interested in environment. You can have a place to work on environment and other things. So this is a short introduction about the Tamil Nadu Science Forum, and we will go ahead with the lecture. Before let us go to the lecture, I'll ask Dr. Shubhasri to introduce the speaker.
It's a great pleasure to introduce to all of you the speaker today, Dr. Sukanta Roy. He's a trained geophysicist and heads the Borehole Geophysics Research Laboratory, Karad, under the Ministry of Earth Sciences, Government of India. His primary interests include research in earthquake science through scientific drilling investigations in active fault lines, borehole geophysics, earthquake geology, seismology, geothermics, and rock mechanics. I'm sure all of this is very interesting to all of you. His recent achievements include the design, planning, and execution of a 3-kilometer deep scientific borehole and downhole investigations, which provide new insights into the geomechanical and geothermal regime controlling the recurrent reservoir-triggered earthquake. So it's very useful research in this present times. I will leave you to attend the lecture. I will not hold you up. Thank you so much for agreeing.
Thank you, madam, for the kind introduction. And thank you, Mr. Vijayan, for having started this initiative. Actually, I would like to congratulate Mr. Vijayan and his team of volunteers who have started this very noble initiative of these popular science lectures. And it is really my pleasure to be here amongst so many students, a full hall of students, which is really a very rare thing to happen. You have such a beautiful facility, the Anna Centenary Library building. Really world-class facility, and I was totally impressed with the facilities that are available here. And I would like to, again, compliment the government of Tamil Nadu for making this facility available. Not many states really can boast of such a building, such a facility, and very importantly, such an audience. So many students in this hall. And I really want to say that I'm very happy to meet all of you. And my guess is you may be mostly from the undergraduates. Please correct me if I am wrong. Engineering graduates and undergraduates. And of course, postgraduates. Okay, great. That is even more interesting. And from diverse fields. And also we have many other friends here from different disciplines. So before I start my talk, I would like to also thank Dr. Ravichandran, Secretary to Government of India, Ministry of Earth Sciences, who asked me to give this talk on his behalf. And so I am here today. Okay. I may have to use this mouse here in the computer to show a few things, so I may be standing and sitting sometimes. So please excuse me for that. I'd be introducing a very different topic that many of you may be aware of, but not really gone deeper into it. For example, drilling. Everybody knows drilling. Drilling in your own backyard, in your own house for groundwater. You may have heard about, and you are definitely familiar with, drilling for hydrocarbons, oil, gas, etc. But I'll be talking today about a non-commercial application of scientific drilling to help us understand certain things about our own home, the planet Earth. So how much do we know about our home, our own planet Earth? What is inside? What are the different processes happening? So on and so forth. I'd like to ask some of you, okay, if someone asks you, what do you know about the Earth, the inside of the Earth? Or what do you want to know? So can you come up with some very common questions? Anybody? What are the common questions in your mind? What would you like to know about the inside of the Earth? Anybody? I mean, it can be anything. Pardon? 5 elements, okay. Yes. So please name the 5 elements. Soil, fire. Okay, thank you. Actually, I would like to hear from the young students here. In fact, last 2-3 days, I was traveling to Chennai, and then in Chennai, I talked to a number of students. What are the different questions that come to your mind when you talk about the Earth? And you will be, I mean, some of these questions I have put down here. How the Earth was formed, how it evolved over time. What is the climate? How it has changed over time. What is the temperature inside the Earth? Everybody knows that when you go deeper and deeper, the temperature increases. How do we know that? How do we measure it? Okay, some of you can say we go deep in mines and it's very hot. Yes, fine. But how do you measure it? What is the internal structure and composition of the Earth? What are the origin of energy resources, water resources, like you said? From where does this energy come? Energy resources like, for example, geothermal energy, or even hydrocarbons and many other energy resources, both renewable and non-renewable. What are the dynamics of the Earth's crust? So has it stayed the same since it was born 4,600 million years ago? That's the age of the Earth. Has it remained the same, or has it changed over time? How do the mountains form? In the oceans, you have subduction zones. So how were they formed? And how they have evolved over time? Then earthquakes, volcanic eruptions, landslides, meteorite impacts. These are very common questions. Okay, how do earthquakes happen? What is the effect of meteorite impacts? What happens when these meteorites hit the Earth? Then, fundamentally, the evolution of life on Earth. I mean, there were a number of questions which came, but I just selected a sample. And to know the answers to all of these questions, how would you know that? How would you get the answers? There's no other way than to ask the Earth. You have to ask the Earth. You have to ask questions to the Earth. And how will you ask those questions? How will you ask those questions to the Earth? You have to set up certain measurements in the Earth. You have to interrogate the Earth. You have to set up maybe some sensors deep in the Earth. So the best thing is to ask the Earth to get the right answers, because as this saying says here, the earth is very knowledgeable, but you got to ask the right questions. Now, so far, what are the sources of information about the earth? How do we know some things? We know a lot. Okay, we don't know a lot, but we also know a lot. How do we know them? We know them through geophysics. Number one, that is to apply the indirect geophysical techniques like surface seismic wave velocities. So you send seismic waves inside the earth, you generate seismic waves through explosions, you send the waves inside the earth, these waves come back after reflection and refraction, and you record these waves, and these waves carry the information about the properties of the different layers inside the earth. Similarly, there are many other geophysical techniques like gravity and magnetic field, electrical field, etc. The other way is when certain eruptions take place from inside the earth, along with the magma, certain fragments of the mantle and deep crust, they come up. And scientists study those samples, those rocks, to know, okay, what's the kind of temperature, what's the kind of composition of the rocks that are present at such depths as in the mantle, for example, 2000 up to 2,900 kilometers. Okay, the Earth's radius is, anybody? What is the radius of the Earth? What is the distance from the surface, from where we are standing, down to the center of the Earth? Excellent. 6,371 kilometers is an average, is a good average. Okay. Now, so these are the ways in which we can get information from. So these are called xenoliths. And the most, I would say, the confirmation comes always from drilling. You drill inside the earth, you make measurements inside the earth, you recover the rock samples and measure their properties in the laboratory. So these are the ways in which you get to know about the earth's interior. And this is a famous diagram of how the earth works. It's called the plate tectonics. And you can see the continental crust, the oceanic crust, how the oceanic crust goes down, subducts below in the mantle, and then you have these trenches, you have the volcanism, arc volcanism, you build mountain building, and so this is a very, very, very common picture, but a very simple picture of how the earth works. Okay, so in today's talk, I would like to cover a few things about this scientific drilling. Okay, the drilling that I mentioned in the previous slide. So what is scientific drilling? Drilling, as you know, everyone knows what is drilling. What is scientific drilling? That is drilling for scientific purposes. Yeah, that's fine. So drilling for the scientific purposes. So you design the drilling strategically, you plan what kind of measurements have to be made, and things like that. What is the motivation? What are the goals, different goals of scientific drilling? So you can actually, it has applications in almost all areas of human life. So you take geohazards, that is earthquakes, volcanoes, etc. You have georesources, that is the resources from inside the earth, be it in the form of energy resources, for example, hydrocarbons or geothermal energy or different other energies. So then you have the critical elements, for example, silicon, lithium. Everybody is using lithium right now on this in this room, in their mobile phones and things like that. So you get these metals, you get these elements from inside the earth. So georesources. Then environmental change. Okay, how has the climate changed? We all know that climate is changing. But what we know from records is over the last 100, 150 years, since the meteorological station records started recording the temperature, the rainfall, etc., the Met stations as we say them. But then, what happened earlier in the earth? Because what happened earlier, the past is a key to the present. And therefore, it is important to know how the climate has changed in the past few hundred years or maybe few thousand years. How do you get to know that information? Today, you know that the earth is warming, global warming, okay. But you have only a reference of about 100 and 150 years to know, okay, fine, you are seeing the graph rising. But did a similar situation exist few hundred years ago or few thousand years ago? How do you know that? You don't know, because your instrumental record is very small. So the earth has very carefully preserved all these records in different forms, and we only have to read the records that come from the earth. Then structure and composition of the earth's interior. Then I'll spend a little bit on drilling techniques, because many of you may be thinking how drilling is done and how do we get the samples, how do we make the measurements. And I'll go through a few case studies, which includes, as Mr. Vijayan mentioned, the deep drilling that has been carried out in India for the first time for scientific purposes by the Ministry of Earth Sciences. So I'll be talking about a 3-kilometer deep scientific borehole that we have drilled. And what are the other research opportunities? So this is basically the outline of my presentation today, and I hope I'll be able to cover at least some of them. So as I mentioned, what is scientific drilling? You can define scientific drilling in different ways. Strategic digging of the boreholes to analyze the deeper parts of the Earth's crust. To applying drilling methods developed in the hydrocarbon and mineral exploration industry to dig holes and retrieve samples of rock and fluid for scientific non-profit, not-for-profit purposes. You can also say that, okay, scientific drilling is simply drilling for research, scientific research goals in land. You can do that in land, you can do in lake sediments, you can do in sea floor, you can do in ice sheets. So in lakes, scientists drill in the lakes to get a long paleoclimate record. Same is the case with ice sheets, because in ice sheets, annually every year, there are certain changes in temperature, for example, that take place, and they are very well recorded in the form of layers. And good oxygen isotope measurements in the laboratory can actually bring out the history of temperature change that has taken place in the past few hundreds of years. But it's how do you get that sample? You need drilling. So there are a lot of applications for scientific drilling which we often tend to ignore, because such drilling is expensive. But then the information that you get is, we call it pakka information. It's true information. So here, if you can see, if everybody can see the slides from wherever you are. Okay, so here you can see what are the different, globally, what are the different areas where scientific drilling has made an impact. So you can see these are the different processes taking place in Earth. Okay, and whether it is in the atmosphere or biosphere or geosphere, there are different applications of scientific drilling. People have drilled in different settings, different tectonic settings, to get information about these processes that affect us, that affect our everyday life. So significant advances to our understanding of the Earth's structure and processes are now emerging from diverse areas. For example, physical and chemical properties responsible for earthquakes and volcanoes, and optimal methods of mitigating their effects. Okay. Then you have the Earth's changing climate and causes that I mentioned. Effects of major impacts on climate and mass extinctions. Everybody knows that there were dinosaurs on this Earth. Many of you have seen that film, right? the dinosaurs. Now, the dinosaurs got extinct about 65 million years ago. How do you get all this information about the extinction? What caused them? So there are different theories. One of the theories is also that a big impact crater, a meteorite, hit the Earth and caused extinction. So I will show some of those results that have come out from scientific drilling. Then interactions of the deep biosphere with the geological processes. So these microbes, the microbial organisms, do you know that they live inside the Earth? They survive inside the Earth under very extreme conditions of temperature and pressure. So it's a beautiful field, and my friends here who are from microbiology, geomicrobiology, they know about it. That, okay, the bacteria, the microbial organisms can survive under exploration of renewable energy resources, safe disposal of radioactive wastes that come out from the nuclear power stations. Okay, how do you safely put them aside so that they don't harm our environment? So you do that geologically. Similar is the case with carbon dioxide, and many of you know today carbon dioxide sequestration. That is, the carbon dioxide that is produced and is by different industries, by different man-made activities, vehicles, everything. That is increasing the climate, the temperature of the Earth. And how to mitigate those effects? You are already seeing the effects of such climate change, but how to mitigate that? So one of the things that people are trying to do is to bury the carbon dioxide deep inside the Earth. But you need to find good locations where they will stay there and they will not pollute the groundwater that you drink or different other resources. So then heat, mass, and fluid transfer, for example, from the volcanic eruptions, and so on and so forth. So scientific drilling provides the exact, fundamental, and globally significant knowledge of the composition, structure, and processes of the Earth's crust, and helps to confirm or reject models based on surface studies. Many of you do surface studies and create models, and you have read different models. How do you confirm those models? So scientific drilling and measurements deep down can give you the data through which you can confirm or reject those hypotheses or models. So I'll not go through, I've in fact gone through the different applications already, but here is a summary kind of thing, that if you take solid earth hazards, earthquake, volcanic eruptions, landslides, they pose dramatic hazards to mankind. And what are the main drivers initiating and controlling their occurrence? How do we distinguish active faults from inactive? So in India, when earthquake happens somewhere, it's always a surprise. Okay, if it is happening in the Himalaya where two plates are colliding with each other, you are not surprised. You know that it's a plate boundary, and you expect earthquakes there because plates are moving past each other. But what happens in places like Chennai or Ongole or Nellore or in the mainland interior part of the country where you don't have plate boundaries? So how do these earthquakes happen? How do you explain them? There are active faults, there are different faults. Faults are weak zones inside the earth. And there is no way of actually taking a imager and taking a picture of or scanning the earth interior through a device. It is not possible. The earth is huge, vast, and it's very complex. Actually, it's many times more complex than the human brain, which people have now found out ways of imaging. But how do you image the whole earth? So how do you know which faults, which weak zones are active and which are dormant? Which weak zones or faults can produce earthquakes? After how many years? We don't know. And this is a very, very complex problem, and that is why we don't have answers to questions like, okay, can you predict earthquakes? No. Today, we cannot predict earthquakes, although the whole world is working on this problem for 100 years. But we don't have solutions yet. So how do we increase our understanding about these processes? So you have to drill in these zones some good select areas and find out, okay, what's the processes going on, what are the changes in different parameters, physical properties, chemical properties, deep down where the earthquakes occur, and how they change before the earthquake, how they evolve, after the earthquake, how they behave, these properties behave. So these are, but then you have to drill, you have to reach those depths, a few kilometers at least, and then you can set up your laboratory there. So then geodynamic processes, how are planet formed? So I have spoken about these things. Georesources, I have also mentioned that for a sustainable planet, the world needs to move to a low carbon economy. And how do you move towards a low carbon economy? For example, you have to use renewable energy resources. How do you get these renewable energy resources? How do you explore them? How do you exploit them? So you need drilling. And then carbon capture and storage. How do you capture the carbon and send it, bury it down, and what happens to it in over a period of hundreds of years? Environmental change, understanding the climate change and evolutionary processes, knowledge of the past environmental conditions, etc. Through so there's a multidisciplinary area that involves geology, geochemistry, seismology, mechanics, many other fields, biology, which are interrelated. And you have to bring all of this information together in order to try to understand how these processes work. So for those of my friends who are studying, say, a particular branch of engineering or a particular branch of science, say biology, you may be thinking that, okay, I don't need to know as I go higher and higher after master's, PhD. I don't need to know physics. I don't need to know chemistry. I'm fine. I'm an expert in biology. Somebody may say I'm an expert in physics and I don't need to know biology. No, it's not right, because all these sciences, their role is to, God did not create biology, physics, and chemistry and different things. Okay, so we made them. So why? We made them because we wanted to understand the nature, understand the processes that take place on our earth. And unless you know about them, unless you have an interest in different areas, you will not be able to explain a process completely. You may be explaining a process from the physics point of view, or you may be explaining the process from chemistry point of view. But in order to explain the process as a whole, you need to interact with experts in different areas, combine those expertises, work together as a team, and then come up with good solutions. So, as I mentioned, the Earth is 4.6 billion years old, 4,600 million years. 4,600 into 10 to the power million years. Million is 6, billion is 9, okay? So it's a long history, okay? And what has happened on Earth? What kind of processes? So these are important to know, and how do we know them? We know them through scientific drilling. Suppose you want to know about certain processes, and you have to measure those processes in the near source. For example, you take an earthquake. Okay, earthquake happens maybe 6 kilometers below the surface. We use seismometers on the surface, and we record those waves, those earthquake waves. Suppose, that those waves actually come from 6 kilometers up to the surface. They come up through different layers of the rocks, different layers of the earth, and at each interface, they change their properties, right? And at the surface, you record them, and you try to say that, okay, fine, I know everything about what these properties are. It is not possible, because it's an inversion problem, basically. It's not a forward modeling problem. It's an inversion problem. So you have the data, you want to know the cause. How do you get that? So you use mathematics. But then, suppose you had the opportunity of keeping that same seismometer, installing that same seismometer at 5 kilometer depth. And an earthquake occurs in around 5, 4, 6 kilometers, 7 kilometers. Then the waves will have a much shorter path to travel to those seismometers. And therefore, the noise will be much less. You will get much more clean records. So there are different advantages of such information, because the lower the noise, the better will be your interpretation. And now, several new horizons of scientific exploration has come up. Now people can drill several kilometers on the land, in the oceans, and on ice. These are extremely challenging, but they are possible technologically today. And many of you have studied some bits and pieces in your engineering classes. It involves all branches of engineering put together and all branches of science put together. So how is the drilling done in continents? You have seen a simple drilling, groundwater drilling in your backyard. Many of you have seen, okay. How do the mineral exploration, how do you get deeper? So this is like 100 meters, 200 meters, maybe 300 meters. If you go to places like Salem, Namakkal, these kind of areas where you may have to go deeper down to get water, okay. So, but how many? Like 300 meters, 400 meters. But if you want to go deeper and you want to get the samples from those depths to do laboratory studies, then you need to do certain kinds of drilling. So what is done is, you use a core bit. What is a core bit? It's a diamond impregnated bit. So it's a cylindrical bit. Maybe, let me see if I have a picture. Okay, maybe I'll show you later. So that bit, maybe I'll talk about it later when I have the picture. So now today it is possible to drill also through the ocean. So you have the water, a few kilometers of water depth, and below that you have the sea floor. So there are ways to actually drill through that. There are ways to drill through the ice sheets. And then there are hyper deep water riserless mud recovery drilling systems also, which can drill really deep holes, 4 kilometers, 5 kilometers holes in the ocean. So all that is possible today. In fact, such boreholes are used for drilling and sampling active fault zones, geological fault zones. They drill into deep permafrost and lakes in the Antarctica, for example. How do you drill? It's frozen in the Arctic. So it's possible to do. People have also drilled now, or trying to drill with partial success in the magma. You know magma, the molten magma. It is the ultimate source of energy. And suppose one day, if we are able to harness the energy from the magma, the heat energy of the magma, which is like 1000 degrees Celsius and upwards, okay. You know, the energy problem of the whole world can be solved. But then, how do you harness the energy? How do you capture that energy and make it useful? It is one of the emerging frontier areas of science and technology. But people have started doing it at places where the magma is at a shallow depth. In Iceland, for example, it is sitting on a mid-ocean ridge. And wherever you drill, you can get very hot waters. Now, if you drill deeper, the magma is actually quite close. Maybe within a few kilometers, you can get magma. But do you think really it is possible to drill into the magma? It is hot, molten. Your drilling system, bits, everything will be, destroyed. How do you measure? Suppose you drill. How do you measure your instruments, your cable, the cable through which you will put the sensors down deep in the borehole? They will all melt. They will all stop working. So, but now technology has come to a point where you can actually start drilling into the magma. With partial success they have done in Iceland, Reykjavik, for example. What they do is, ahead of the drilling bit, they keep on circulating water, cold water. And that is the way they have started reaching those supercritical fluids. So, a very interesting phase lies ahead. Now, how much deep have we gone so far? Anybody knows what is the deepest hole on Earth? I'm sure someone. Pardon? Very close. 12 kilometers closer. So yes, 12 kilometers, 12.2262. 12,262 meters is the deepest that man has drilled on Earth. And it is in Russia. Okay. So you can see if you 12.626 kilometer, then in Germany you have the 9 kilometer deep borehole, 9.1 kilometer. They call it the German super deep borehole. This is the Kola Peninsula in Russia, so Kola super deep borehole. Then you have in Oklahoma, this is for oil. Okay, in South African mines, gold mines, they have drilled up to 3.5 kilometers. So in oceans, they have drilled up to 2,111 meters below the sea floor, not below the surface, below the sea floor. And in India, we have done a drilling up to 3 kilometers below the surface. Okay. But really speaking, if you see the interior of the earth, and you know, some of you already said, 6,371 kilometers is the distance from the surface to the center of the earth. So how much have we drilled? What is the deepest hole? It's only scratching the Earth's crust. It is only scratching the Earth's crust. The Earth's crust, continental crust, is about 30, 35, 40 kilometers thick. You have drilled up to 12 kilometers, which is only a 1/3 of it, right? But even such technological challenges have been overcome, and they have drilled, and the information that has come out are completely new and surprising. And I'll show you some of those surprises. Now, what are the challenges in drilling boreholes? First is the geology and the rock type. Whether you have soft rock, like in the oil basins, whether you have, thank you. So whether it is soft rock or hard rock, okay, like granite, basalts, or sediments, so the drilling challenges are different. Then what is the depth that you want to drill? The deeper you go, the more complicated it is, very common to understand. Then if you have these fault fracture zones, so these fractured horizons, then drilling becomes very difficult because your drilling rods can get stuck in those fractures, and through the fractures actually a lot of fluids, water can come in, and it can really hamper your drilling progress. So there are a lot of challenges. There are many other challenges, like suppose you want to drill vertical. Now the verticality, to control the verticality, or you want to drill at an angle. Today everything is possible. You can drill any shape, any configuration you want, but you have, those are the challenges. How would you direct? So you have to use directional motors and things like that. How do you core? How do you take out samples? How do you core from such depths? I know that, for example, when we drilled the 3 kilometer borehole, to take out the core from such depth at 3 kilometers, a 200 kg piece, to lift it up, cutting is anyway a challenge, but to lift it up to the surface was such an exciting sight to see and experience. Then you may have different overpressured zones in this below the, then you have to do different kinds of measurements. So your measurement tools have to, so it needs a lot of planning to actually get into a good drilling exercise and get a healthy borehole. Because whatever measurements you want to do, drilling is not the goal. The goal is to actually use drilling or use the borehole as a tool to do science. And therefore, you need a healthy borehole. You need a borehole which can actually deliver you those requirements. And then if you want to install boreholes, sensors in the hole at those depths, then that is also you have to keep in mind before you actually design or plan the borehole. Okay, so here I am showing you some drilling techniques. For example, I spoke about the drilling bits. And if you can see up close on the top left, those are the coring bits. So the top of those bits are actually diamond impregnated. That means, you know, diamond can cut hard rocks, okay? So those kind of tools are used. Now, when you send these core bits down, and then you apply rotation as well as pressure from top, then you slowly start cutting these. And then once the cylindrical core is cut, you can get it up through wireline techniques. There are other methods of drilling. For example, if you don't need the cores, then you can crush the rock. So these are called down the hammer drilling. The above, the first one was diamond core, diamond rotary drilling. This is called down the hammer drilling or percussion drilling. So you use the air, the pressure of the air is basically to pound the rock, to rotate it, to crush it, and then lift the cuttings up. So when you do this, if the rock becomes powder or chips and settles at the bottom, definitely it will settle at the bottom, and then you cannot drill further. So continuously you have to have a system of taking these cuttings out. How do you do that? So you send water under pressure inside the drill rods, and then from the annular space between the drill rods and the borehole wall, you force these cuttings out to the surface. Unless you do that, you will not be able to drill further. So these are different challenges. And then there are other bits, like if you do in sedimentary formations, in sandy formations, for example, then you need these tricone bits. So the different bits for different purposes. And once you drill, then you have to, during drilling, the other important thing for engineers especially, even if you have taken a saw and cut a rock or something, have you done that? You must have done somewhere. It generates a lot of heat. So how do you control that? So you put water, right? You have a supply of water, right? You must have seen in different rock cutting. So here also, what is done is you send a drilling fluid inside. So the drilling fluid, it's water and some clay minerals and things like that, which has two purposes. One is to cool the drilling bit, and the other is to get these cuttings out, to get the rock powder out. So you need certain properties called thixotropy. So the rock powders will be held in suspension in such a fluid, and therefore when you apply pressure from the top and you get these cuttings out through the annular space between the borehole and the borehole wall and the drilling rods, you actually ensure that these drilling chips, they don't fall back below. So that is why you need such thixotropic property of the drilling muds. So then once you drill the rock, you may have to case it to save it for the future, to cement the casing and things like that. Okay, so I will show you one real example of a large format drilling. This is an example from our own drilling that we carried out, 3-kilometer borehole drilling. So 3 kilometers is a very challenging operation, and if you see, this is a drone picture of the drilling exercise that we did in Koyna area in Maharashtra, where we are located. So you can see how much complicated, what different kinds of accessories you need. You need such a big drilling rig. You need air compressors. You need mud tanks for mud. You need generators. You need cementation tanks. You need filtration tanks. You need to, if you want the gas to, if you want to analyze the gases and fluids that are coming out from the borehole during drilling, then you have to have a gas separator or a fluid separator which separates the gas from the cuttings which come out. So it's a huge operation if you want to drill a 3-kilometer borehole, and many of the oil wells are drilled in this fashion. So you now know, okay, what it entails, what it takes to drill such deep boreholes. And these take several months. For example, this one, to drill a 3-kilometer borehole, all of us, the drilling crew, the scientists, the technicians, everybody had to be at the site for 8 months. We had to remain in the drill site in this area for 8 months, under all kinds of weather conditions, monsoon, winds, everything. But that is because drilling goes on 24/7. And therefore, but then, at the end of it, so these are, you may be interested, these are the white ones are the accommodation, the containers which were converted into our accommodation. So shift-wise we work, and then we also have some resting place and things like that. Okay, so you got some idea about what it takes to do drilling. So this shows the progress of drilling. So as you go drill, and then you do different measurements, so you stop. So then you take core samples also from different depths. Suppose you need samples from certain depths. So you stop the drilling and then do a core recovery. So coring is another operation. And then you have these in-field laboratories. So geological laboratories, mechanical laboratories, mud logging laboratories. All these laboratories are there at the site. And people are working there 24/7. This is a coring one. How do you take out core samples? So you can see this core is 4 inches in diameter. And you are taking it out from a depth of 3 kilometers. It's an amazing feat, actually, when you finally get the core sample out and put it up in your laboratory. You know that, okay, I'm touching a rock which has come from 3 kilometers depth. 3 kilometers. The distance from Anna Centenary Library building to, can you say how far is 3 kilometers? Anybody? Guess? Pardon? Gindi. Gindi is 3 kilometers? So you take the distance from Anna Centenary Library to Gindi, and you convert it into depth. Now you know how deep you have gone. And to get a sample from there, it's like getting a sample from the moon, isn't it? Many times, actually, people call these deep boreholes as downward-looking telescopes, because these allow you to look down, downward-looking telescopes. You can send a rocket up in the space, but how do you do that inside the ground? You have to do this. So these are the different stages in which a core comes out, and then it is cleaned, washed, and see, these are the kind of cores, granite core, which has come out from, if you can read, maybe around 2,500 meters depth or so. And then they are marked, and then they are curated. So we have a digital optical scanner which can take a 360-degree whole round image. So 0 to 360-degree, you can have an unwrapped image, and you can study the different features on the core. And you can join these pieces and create your own borehole column. And for example, how are these cores preserved? Because these are very expensive. So for example, in our own institute, we have set up a core curation facility, a core repository. What we call it as a core repository. A big core repository where, like a library, we preserve the cores, the physical cores, in tin boxes or wooden boxes, catalog them just like you would do in the case of the books. And then scientists, researchers from all over India, all over the world, they come, study these samples, take away samples for their own measurements, and find out new things about the interior of the earth. This is how science progresses. Once you have the borehole, you can do measurements in them. So this is how a very simple picture of sending tools inside the borehole. In such deep boreholes, this is not the way. You have to do it using cranes and many other big instruments, equipments. But then, basically, you have to put these sondes or probes down in the borehole. You can have a sonic probe, you can have a density probe, you can have a porosity probe. You can measure whatever. If you want to measure the electrical resistivity, you can have an electrical resistivity probe. You send them, and then have a continuous measurement down up to the bottom. And then you have these beautiful data, the plots of different physical parameters. For example, self-potential, gamma ray, log, velocity, S-wave velocity, P-wave velocity, shear anisotropy. You have neutron porosity, density, you have the resistivity, and different physical properties, whatever you name it, is possible to measure today, magnetic susceptibility, etc. And then, beautifully, actually, you can actually do the entire borehole image, not using a simple camera, but using acoustic technology, using formation micro-resistivity technology. So you can get beautiful images of the borehole wall. So if you have not able to take the core samples throughout the borehole, you can actually get these high resolution images of the borehole wall. They are like cores. So you can study the fracture patterns in them. You can study different features in those images. There are different tools which you can send down, and they all perform different functions. Then once you have a borehole, you can do experiments in the borehole. So you can put sensors in the borehole. You can generate an artificial earthquake by a vibration on the surface and record those waves inside the borehole, in the instruments that you set up inside the borehole. So different kinds of things are possible. Then if you drill a borehole, you can have a borehole observatory, a deep borehole observatory. So this is a schematic example where on the surface you have all the recording instruments, and you can really have a string of different sensors inside the borehole, and you can measure different parameters continuously over time. So you know how these parameters change with time near the zone where earthquakes are taking place or some other physical process is taking place. So this gives an enormous step forward, advancement to science, which was not possible before we were able to drill such deep boreholes. Right? So one of the challenges now to the young engineers is to devise new instruments, new sensors, which can withstand the temperatures and pressures at those depths and do a digital recording of the parameters for tens of years, 10 years, 20-year period. That will be the biggest, you can say, step forward in our understanding of these processes like earthquakes. But right now, many of these sensors fail, and so there is so much of research opportunity for you, young people. Don't sit only with your computers, but also think about these problems. Okay, if you develop these sensors, if you develop the tools how to measure the properties in temperatures like 100 degrees, 200 degrees Celsius, 300 degrees Celsius, over 10 years, will that digital electronics withstand those temperatures over time, pressures, things like that? So these are beautiful opportunities which are coming out because we now can drill deeper and deeper. Major international scientific drilling experiments have taken place. Okay, then I'll cut down, yeah. So world over, you can see such beautiful experiments, scientific experiments have taken place in different continents, in different settings, on land, in ocean, in ice, everywhere. And we have come out with some really exciting results. So many of you told that the deepest borehole is 12.26 kilometers. So this is a picture from that site in Russia, the Kola Peninsula. And you can see the drill rig. This is a 15,000-ton capacity drill rig, which was used to drill this 12.2 kilometers borehole. And they had actually to stop the drilling because the temperatures became so high. And you know how much time it took? They started in 1970, May 1970, and it went on up to 1990s. So more than 20 years they took. They failed, they tried, failed, tried. They did everything. And finally they went up to 12.26 kilometers. Enormous, 12.26 kilometers from here to airport. I don't know. How much? 12 kilometers. Just think. So it's there are beautiful movies on that, Journey to the Center of the Earth and things like that. You can see on these movies. So this was no less because humans have persevered and gone to such depths to know what is inside. And you can see the temperature profile. You can see what temperatures they encountered at 12 kilometers, roughly 220 degrees Celsius temperatures, 220 degrees Celsius. They wanted to know how deep the ore deposits, ore deposits, iron ore, copper ore, so many ores, up to what depth they can exist. So they tried to find out, okay, let us drill and find out how deep we can find these deposits. Then composition and physical character of the rocks at such depths. Then this transition zone. What they wanted to know is the transition from the Earth's crust to the mantle. So they wanted to know what is the mantle looking like. So they wanted to drill through the crust, the base of the crust, and go into the mantle. They did not succeed because the crust was much thicker than 12 kilometers, and they could not drill any further with the current technologies, 220 degrees Celsius. And a lot of cost had already been involved there. So, but finally, when they achieved this, they were able to take out 4 kilometers of core samples from such depths. And they came up with the data that this borehole was able to provide, brought up so many surprises. Everybody knows in hard rock, if you go deeper and deeper, the pore spaces close down, right? There is no water. If you go kilometers deep, you may not find water. No, but that's not true. This was the first experiment in the world which falsified that hypothesis that there is no water at depth. Even up to 12 kilometers, they found that there is permeability and the fluids circulating through the crust. I'll take the other example of the German super deep borehole, 9.1 kilometer. These are like historical landmarks, 9.1 kilometer deep borehole. I have actually visited this site. It is in Bavaria in Germany, where they have developed a tourist spot now. You can take groups of students or groups of public. They can take appointment, go there and go through the entire facilities. It's one of the most exciting things to do, I can tell you. And some of you, if you have an opportunity to study abroad or go abroad, you can actually go for such sites. So before these deep boreholes, people did not know what the structure of the earth was looking like. So anybody could paint any picture. Like here is one picture. Okay, we have no idea what it is inside, what it looks like. So you can paint any picture. But once you have the borehole, so this was the drilling rig that stands even today there. It was drilled in 1990s, but it is standing there today as a monument. And they have found so many surprises. Again, fluid percolation along extensive fracture pathways down to the mid-crustal levels. So it's not true that fluids don't exist deeper in the hard rocks. Surface geophysics. Geophysics uses instruments at the surface and then tries to get the image of the inside of the earth. But these are all modeling exercises. So you get the data and then you do an inversion, mathematical inversion, and get the story, get the image. But then once you have such deep boreholes and you have the measurements down to those places, you can actually test these models, test these hypotheses, whether they are right, they are wrong, or they are partially right. You don't know. What is the temperature gradient at such depths? 9 kilometers, 12 kilometers, these are like 1/3 of the Earth's crust. And there is no other way you can know the temperatures. You have to measure. And now we know what are the temperatures, at what rate the temperatures increase as you go deeper and deeper. So they were also able to measure in situ stress. You know, stress is one important parameter that controls the earthquakes. So there were a lot of surprises and a lot of new knowledge that have come up from these scientific drilling exercises. You can see the temperature. And this was the predicted, but the actual measurements, they exceeded these temperatures. And here also, they had to close down the drilling because the temperatures they expected were much lower than what they actually got, and therefore the technology stopped working. So, but then these are the big advances in science. So if you take the uranium, thorium, potassium distribution with depth in a 9 kilometer borehole, who will give this information? So here you have a direct measurement of uranium, thorium, potassium, how they change with depth through the different layers. And these have a lot of other implications. And I said that this has become a tourist spot now. So this is what the KTB site in Windy Station back in Germany looks like. So they have classrooms, so you can see to reach this is the drill floor. This is the drill floor where the operators sit and they do the drilling. Even to reach there, you have to actually climb. You have to climb a lot. Drilling into magma, I told you about drilling into magma. So this is an example from Iceland, drilling into magma. Then oceanic crust, ophiolites. Ophiolites are remnants of the oceanic crust. So they tell us about how the oceans evolved, how the seafloor evolved. And these places are also exciting because they tell us about the Earth's history. So in Oman, they have a beautiful ophiolite complex which they have drilled. Then in China, they have drilled to get continuous high-resolution climate records and then climate change records. Because they take this core, 5-kilometer core, they analyze each and every layer there, and then convert it into time, geological time. Okay? For example, what was the climate during the last 100,000 years or 50,000 years? How do you get them? So you get like this. Then drilling in volcanoes, things like that. So I'll touch upon quickly the experiment that we did in Koyna in India. This is India's big scientific drilling experiment, which was done in a few years ago by us. And the idea was to study about earthquakes. And so this is the region in Koyna, for example, where we have a different kind of earthquake. Earthquake that has been triggered because of the water reservoirs. Water reservoirs, dams. They are very useful for the country's economy. Flood control, irrigation, besides generation of hydroelectric power. The Koyna Dam, the Koyna hydroelectric project, contributes 2,000 megawatts of electricity to the national grid. So you can say it was the heartline of Maharashtra. But then, after such a big dam was impounded or filled in 1962, there was an earthquake activity which increased dramatically. Okay, and this is a very interesting problem. It's called triggered seismicity or anthropogenic seismicity. That means man-made seismicity. And you have different examples. It can be from such reservoirs. It can be from mines. Deep mines. Kolar gold mine, for example, 4-kilometer deep mines. So you excavate and take out the materials. So that can also cause some seismic activity, like in South Africa. Then you inject wastewater into the subsurface and to do the secondary oil recovery. For example, how the oil reservoirs are. So the easily extractable oil has been already taken up. Now the oil that exists there are deep into the formations. So how do you get them out? So you have to inject water at great pressure from the top, and through another hole, you have to get the water out, get the fluids out, oil out. So this is another very big story. But then, in doing so, you have to create certain fractures called hydrofractures, hydraulic fractures, fracturing with the impact of the water pressure from the top, from the surface. So these kind of things they generate. So these are all very useful scientific engineering exercises. They are all extremely important for the country's economy, but they all have certain consequences. And how do you mitigate such consequences? How do you understand such consequences? So this is one experiment where we have been trying to do that. Now, if you want to know about earthquake genesis, how the earthquakes formed, because I told you in the beginning, we can't predict earthquakes. It's very difficult. It's really, really difficult, because we know so little about them. There are so many kinds of earthquakes, different kinds of earthquakes in the world, that we really don't have enough data. Now, what are the kinds of things which will give you the information, the control on understanding the processes? You need a lot of information. You need structure deformation in the below the surface. You need the stress information. You need temperature. You need permeability, how permeable the rocks are, the fracture patterns, the fluid chemistry, the fluid pressure. It's an interdisciplinary arena. Interdisciplinary arena, physics, chemistry, biology, mechanics, geology, geochemistry, many things put together. And so these are the controls that you need, and you cannot get these controls without scientific drilling. You cannot get them. So until you drill and you measure down there, you will not be able to get a control on the handle. You will not be able to understand these processes completely. But many of these measurements actually you cannot do in the boreholes also. So you have to take out the samples and measure in the laboratory. So to take out the samples from such depths also, you need to do drill. So this was the pilot borehole that I showed you earlier. So these are the kinds of rock samples that we have got. Now you can see these are different kinds of deformation. When an earthquake happens, you know one rock slides past the other, vertically, horizontally, and in different angles. And when they do, they form slicken lines, they form striations, linear features. If you look closely, there are striations, the linear features on these surfaces. And there are many such signatures of the earthquake. For example, here, before an earthquake, this band, white band, quartz band, was continuous. After the earthquake, so this part has moved here, this part has moved relative to this block on the other side, and therefore there is an offset. Can you see the offset in the white band? So these are the effects of movement in the earth, and they might have been caused by earthquakes. Then there are melts. When earthquake happens, friction, due to friction, momentarily for a few seconds, the temperature rises enormously. Enormously. It actually melts the rock. And those melts are these black materials that go into the fractures, into the injection veins. And then there are so many other examples I'm not going to go through in detail today. But you can get this information if you drill and take out the core samples. You can know about the physical properties through the different logging measurements, through the measurements that you do in these deep boreholes. You can find the evidences for water. You can find so many other things from these geophysical logs. These are called geophysical well logs. That means the geophysical properties, physical properties of the earth, geophysical, physics of the earth. So you measure these physical properties, and you can have a continuous record of them from the surface down to your final depth of the borehole. Okay. Then you can analyze the gases that come out from depth. Different gases, methane, helium, and many other gases, they come up from depth. And if you study those gases, you will know what is the geochemical formation like, what are the geochemical properties like. For example, helium is an inert gas, and the concentration of helium in the atmosphere is fixed, 5.24 parts per million. Okay? But over such faults which hit the surface, or over different geothermal reservoirs or oil reservoirs, if you measure helium, you will get peaks. And those peaks, for example, here in our borehole, we actually measured, these are the peaks which mean that at those depths below 2 kilometers in Koyna region, there are fractures, there are faults. Then we measured temperature. What is the temperature? How much, you have all studied temperature in the textbooks. What is the geothermal gradient like? How much does it increase if you go down 1 kilometer? Thoda jor se. 25 degrees Celsius is a good average. Somebody will say 30 degrees Celsius. But these are average numbers. And these change from place to place. These change from place to place. And here, for example, at 3 kilometer depth, we measured a temperature of 80 degrees Celsius, 78 to be precise, 78 degrees Celsius. Then we measured the uranium, thorium, potassium concentrations through the Deccan basalt rocks and the granitic basement rocks. We measured the stress field. So, this is also another engineering discipline. How do you measure stress from the wellbore failures? So, there are different weak zones inside the borehole, and they are really controlled by the stress regime. And if you measure these, you will be able to know the orientation and the magnitude of these stresses. You can get this stress tensor. So, a lot of new information can come from these rocks. You can actually do a hydrofrac test by sending packers inside the borehole, isolating the zones, and then inject water pressure into those zones, and then fracture the rock, and measure the stress orientations. And then finally, you can study the images and do a correlation between fracture, stress, and the orientations of the fracture and stress, and you can actually get a hold on whether this region is susceptible to earthquakes or not. Finally, for example, in Koina, for example, I'll give you one example that we have got so far. We now know that there are favorable conditions for earthquakes to take place in this region because of the critically stressed water-saturated fractures at depth. And small changes in fluid pressure or frictional strength could provide the necessary triggers for failure. So they keep on failing. Almost every day you have earthquakes in Koina of different sizes. Now, how do you explain them? So we are able to explain partially through our data sets from this borehole that, okay, there is geologically a favorable condition here, and small changes in stress caused by either the reservoir load, that is the water load, or coefficient of friction. Everybody knows coefficient of friction, mu, right? So it is now also important, once we know this, it is important to measure the friction. So you can take these rock samples out, you can measure the friction in the laboratory and find out the coefficient of friction. You can do, infinite possibilities for research, for science. Then you have these impact craters that I told you, asteroid impacts. So this is the largest impact crater on Earth, the Chicxulub crater in Mexico. And the radius of this crater is 200 kilometers, as you can see. This impact event led to mass extinction, dinosaurs extinction. Why? Because when this event took place, the ejecta, the ashes, the other things that came out of you can see how an impact crater actually affects. So this impact crater actually penetrated the whole crust and went into the mantle and then brought up the different ejecta, the particles from depth. And by studying these particles, you come to know so much more about what these asteroids, these meteorites were, their source, composition, etc. And then finally, you can get, through drilling, you can get the rock samples where you can study their different properties. And then what happened? What did this impact event do? This impact event actually, if you look at this is the global average surface temperature. So the impact event happened at this time, okay? This is number of years, and this is degree Celsius. So you can see in 2 years, the surface temperature of the world dipped. And then it was there for almost few years before it picked up again, and now the surface temperature, you see this record. These are fantastic records that tell us about the history of the Earth. And what happened, what would have happened? Can you imagine if surface temperature dropped to those levels and the atmosphere was completely filled with all these ejecta particles? It was dark. And if it was dark, what would have happened? Can you imagine? Cold and dark, no life. No life. And if you see this, for example, the food chains before impact, and for 5 years, there was no sunlight, no food. So these dinosaurs and many of these animals, they died. They became extinct. Some other organisms which were able to adapt, they survived. But the dinosaurs and many big animals, they died. And then finally, sunlight returns, and then slowly things start getting back again. So these are reconstructions, these models. How have they come? They have come from such drilling exercises. There is no other way you can actually get such information. Similarly, microbiologists. There are many biologists, I am sure, in this classroom, in this hall. So if you know that microbes exist in depth, and people think that, okay, with increasing temperature and increasing pressure, porosity decreases inside the earth, and the number of cells actually goes on decreasing quite rapidly. But then there are microbes, there is life at depth under conditions of 100 degrees Celsius, 80 degrees Celsius temperatures. How do they survive? Because photosynthesis goes down. There is no photosynthesis happening here. So how these life, these nutrients, how do these organisms get their nutrients for survival? It's a fantastic problem in science today. It's a fantastic problem. So I'll not go into more detail, but I want to say that colleagues from the IIT Kharagpur, for example, biotechnology, they have worked on the samples from the Koina, deep samples. They have come out with exciting new results. For example, these. So there is a lot of diversity and distribution of microbial life within the granitic crust. And we are now able to understand the significance of deep life in biogeochemical cycling. And that can be very useful in carbon capture and sequestration, waste repository remediation, and biodiscovery of novel enzymes or molecules for industrial use, for controlling wastes. There are so many applications. Many of you probably know it. So if you look at this sphere of science, scientific pursuit, you know how multidisciplinary this is. And this is one example where no science discipline has been left untouched by this deep biosphere, by the microbial life that exists under such conditions. So I'll end here today with the outlook, as I would like to, I love this statement, the scope of scientific drilling and applications of borehole geophysics are immense and poised to grow rapidly as both industry and the academia realize their potential to provide cost-effective solutions and direct information on the processes that are operating at depth, and they are controlling the processes that are taking place on the surface, controlling our lives, controlling our existence on Earth. They are controlling our existence on Earth. We must make effort to know them, and we must do such exercises in the future. So it's a multidisciplinary field, and all of you sitting here, no matter what discipline, you can actually participate in such programs. And I'll close this, and for all of you to read this and enjoy this statement. You know, books are written by men and women, but they are sometimes wrong. We know that. They are sometimes wrong. And we are not ashamed of that, but they are sometimes wrong. But the rock record in the field is always right, if you can read it correctly. If you can read it. How do you read it? You have to ask questions to the earth. You have to set up different experiments, so the earth will give you the answers. With these few words, I would like to thank all of you here again for such a patient listening. This is one of the very rare circumstances for 1 hour or more you have been with me listening to this, and I hope very sincerely that many of you would actually take up different problems related to the aspects that were touched upon today in the lecture. Thank you very much.
Excellent, excellent, sir. So we get a exciting lecture. It was a deep insight into the inside of Earth. Excellent, very good. Thank you very much for you. Thank you on behalf of Tamil Nadu Science Forum. Now the Anna Sentinel Library want to honor you by providing you a small memento by Mr. Selva Perumal.
I must say that speaking to such a wide audience is itself an honor, and I can't say it in more words.
So unfortunately, the chief librarian, Dr. Kamachi, is not available. She is sitting in a meeting. She sent Dr. Selva Perumal to. They don't want to miss anything. So now we are going to get into the question answer session. Before we get into that, I have a couple of announcements. Please leave your feedback. No, we have a QR code displayed on the outside. Just scan it. You will get a Google form. Fill up your feedback. That's very much essential for us to improve our activities in future. Please do it. Yeah. Those students who want to get the certificate for attending this event, you have to fill up the feedback form. Upon filling up the feedback form, you will automatically get your certificate of attendance. That's also another another bit. The second thing is, now we are going to have 3 successive lectures on Nobel Prizes. As you know that Nobel Prize is going to be announced on first Monday of October, starting from first Monday of October, second Monday, first Tuesday, Wednesday, Thursday, like that. It starts from medicine. First thing will come out on medicine, the second Nobel Prize on physics, third one on chemistry, like that it will go. So Tamil Nadu Science Forum used to conduct the Nobel Prize lecture on the same year, within the same month, to what makes the the scientists, how did they make the difference, and what is the breakthrough he has made, or he or she has made. So that lecture will be held in this library. And this year we are going to announce, have a small competition among the students, whoever may be participating. So you can guess who is going to get the Nobel Prize and what is the subject they are going to deal with it. So people who are guessing it more accurately, they will get a good prize in terms of a book or some scientific kit. So that is the announcement. We are going to float it soon. Please take note of it. Watch our announcement in the Google group as well as in other social media. Take a look at it, and the last date for submitting your Google form is 7th of this month, because 6th of this month. From 7th onwards, the Nobel Prize is going to be announced. So please take part as much as you can. Try. From next year onwards, you track who is doing which work, and finally you can get into you can reach that. That's another thing. So with that, and I strongly encourage you to become the member of Tamil Nadu Science Forum. Leave your address and mobile phone address and your contact details there. So we will include you in the Google group for to communicate our future activities. Thank you, sir. Let us go to the Q&A form. Obviously, it's going to be reduced because we thought that 45 minutes lecture and 45 minutes Q&A. But since we benefit more out of carving out some of the time from Q&A, because we take a little bit more time, we got more information on your earth sciences. So let us go to the Q&A session. Who is going to? So you can ask your question quickly, sharply, so that we can complete the session as well as possible.
Hello. So hi, sir. That was a nice lecture. So I was admired by your concept of carbon sequestration and storage that you talked about.
Can you speak a bit louder, please?
Can you hear me?
Yes, now it's okay.
I found that the concept of carbon sequestration and storage in the underground that you spoke about is very interesting and promising for the future. I think climate change is a very big thing to be addressed. My question is, you said that there are a lot of factors that plays a role while identifying a location to store the carbon. So what are those factors? And India being a developing country looking for opportunities, does India have such promising locations? What are the opportunities and challenges with respect to India? Like if is there any challenges like carbon leaks, which can be a catastrophic effect to the local community, or opportunities where in Europe there is the emissions are being priced at sometimes at $100 or plus for every ton of carbon dioxide equivalent. So does it provide an opportunity for India? And you talked about carbon capture and storage. What about carbon capture, transportation and storage in some other place on the earth? So who are the potential clients for India? Or let's take even Africa, which is an underdeveloped area. So what are the opportunities and challenges that you look forward when it comes to this?
Thank you. This is a very good question, in fact, and a very timely question. Again, this is a multidisciplinary area, and I will touch upon some points that are related to geology and geophysics. The straight answer to your first question is yes. There are opportunities for carbon dioxide sequestration in India. And what are the your second question was, what are the parameters, what are the things that you need to know? So what are the controlling factors? So number one, because you are planning or you are attempting to bury the carbon inside the earth, you have to know exactly what are the rock properties. Okay? What are their mineral composition? Because simply storing the carbon dioxide inside the earth is not going to help you. If you actually convert that CO2 into certain minerals, into certain carbonates. So mineral carbonation studies are going to be extremely important. So you have to take these rock samples, and the best examples or the most talked about in this area are the basalts, the flood basalts, which have formed, which are igneous rocks formed out of the cooling of the magma during the volcanic eruptions. For example, Maharashtra and a large part of Madhya Pradesh and Gujarat, they are covered with Deccan basalts, because the Deccan eruption took place, the Deccan volcanic eruption took place 65 million years ago. And these rocks have cooled, and they formed these black rocks that you see in most parts of Maharashtra and Gujarat. Now, these basalts have certain chemical composition. They have olivine, and they have certain other minerals which are extremely, which are thought to be extremely adaptable for converting the carbon dioxide into different forms and storing them in the subsurface. Okay, so mineral carbonation, the rock type, the mineral geochemistry, the mineral chemistry is important. The rock chemistry is important. And then the second question that, in the continuing on that, you also have to make sure that the carbon dioxide doesn't leak out at other places. Okay, so you have to know what are those depths at which the CO2 can become supercritical. So you have to go to such depths, so to reach those depths and bury it there rather than near the surface. There is another thing, that is, when you inject the CO2 in the subsurface, you will see different effects with time as you go on injecting it. Laboratory experiments, simulation exercises have shown that there is a balloon effect. There is a balloon effect. So you have to see, you have to control you have to know the different physical properties of the rocks below. You have to know where are the fractures, what are the formations in which you can actually store the carbon dioxide. For example, if you take basalts are of two types. One is massive basalt, the black, hard, massive rock, which doesn't have any pore spaces, practically. The other variety of basalts has a lot of pores and vesicles, which are formed because when the magma came on the surface and cooled, the volcanic gases escaped through these rocks and they created these void spaces. So those vesicular basalts may turn out, I cannot say exactly because many studies are going on, but those formations may turn out to be really good places for storage if the mineralogy is right. And so a large number of groups worldwide and in India, they are working on these problems. Even I can tell you that a number of research groups from India and from other countries like Australia and Germany and other, they have come to our core repository, taken samples for such studies. So a lot of information is likely to be generated in the coming 1 or 2 years, and then we will be able to answer your question more completely. But yes, it is possible in India. Transportation, I think that's a more tricky issue, but that is very relevant because you need to have industries that produce carbon dioxide nearby in order to try this out, right? Suppose you have a big industry in Delhi and you want to store this carbon dioxide in Maharashtra, you have to transport through, and that's again quite tricky. So I think that's a far goal. But the first information that we need are what are the rocks, how are they suitable, how would this carbon dioxide stay there for geological time without impacting on the surroundings. So these are the first questions that need to be sorted out. Thank you.
Yeah. We will have a very limited time, and because the library is getting closed,
Okay.
we'll have a couple of questions. So what I'm suggesting is all of you become the member of Google group. You can post all your questions so that I can forward it to Dr. Sukanta Roy and he will respond
Absolutely.
to your question. So that's possible. Please ask. We will have only 2 or 3 questions.
First of all, thank you very much for a very informative lecture. Though I was very fascinated when you showed how the dinosaurs became extinct. Could you elaborate on the theory of natural selection, which was forwarded by Charles Darwin, which now we don't have the opportunity to look into dinosaurs. So what you showed, it triggered my interest.
Yes, you will have to talk to a biologist to get a good answer. But all of us know Darwin's theory, the survival of the fittest, right? Now, but all the different life on Earth, the different fauna that you find, they all have different adaptation capabilities. And the dinosaurs may not have been able to adapt to those circumstances. So, I mean, I really cannot give a more detailed answer to your question. But certainly the environment played a big role. The absence of light, photosynthesis, food chain was spoiled. But then certain other organisms did survive. So I think it has to do with the adaptive capabilities of different organisms.
Hello, sir. Thank you, sir, for your insightful lecture. Sir, I'm just curious if there are any upcoming or underway projects about this ophiolite scientific drilling in India.
Not in India. In India, there are ophiolites. If you go to the high Himalayas, where the Indian plate collided with the Asian plate, the Tibetan plate. So there is a Indus suture zone. You know that? Have you heard about the Indus suture zone? So India and the Indian plate and the Eurasian plate, they stitched together and formed a suture. Suture is basically a stitch, right? So in that zone, there are occurrences of ophiolites, because it was considered that at one time there was a Tethys ocean, right? So there are certain, but then no drilling has been attempted there. In those regions, it is also very difficult to drill, because if you have gone to Ladakh, where the elevations are of the order of 4 kilometers. In Chennai, what is the elevation? You are close to sea level, right? But there you are above 4 kilometers, 4,000 meters. And there, both man and machine get fatigued very easily. You are talking, I am talking here, we cannot talk like this there. We have to get, we will get tired, exhausted. So machine also has fatigue. So drilling such exercises are really challenging there, but it is not impossible. Not in ophiolite, but on the other side, in China, for example, there is a lake, Namco Lake, where a drilling exercise has just started. And it may be interesting to see if there are any ophiolites there. I don't know, but it is a very good question. There are other ophiolited complexes in the world. Are you a geologist? Okay, good, good. So you should try to find out the different projects that are carried out by the International Scientific Drilling Program, ICDP. You can see I have referred to ICDP on many of these pictures, because these are the international projects which have been supported by the International Continental Scientific Drilling Program, and India is a member of ICDP. So if you have any interest, if you find such a program, and if you have any interest, you shoot off an email to me. Can I write my email address somewhere? Maybe it's, pardon? I can do that. So, and then I will try to connect you, if possible, to some good groups which are working on ophiolites. It's a fantastic problem. It's a very good problem. So yes, surely I will be very happy if you can actually work with one of those groups, yeah. But I will also find out whether there are any groups working on ophiolites right now, because this Oman ophiolite drilling took place 2 years or 3 years before. And they are still working on the samples. So whether that's possible, I'll find out, sure. But you drop me an email so that I have your address.
I should first thank you for an inspiring lecture, sir. Really excellent and lucid, really very inspiring. Especially for youngsters, it will be really very inspiring talk. I'm really very much thankful to you.
Thank you very much, sir.
My question is,
I was equally pleased to talk here, and fantastic audience.
my question is that you were just talking about the Koyna Dam and the associated seismic instability in the potential of having earthquake possibilities here. Then we cannot do away completely dams. Completely, it's not possible here. But there should be some sort of cost effectiveness in the sense, okay, though we have got seismic instabilities here, we can allow it here.
Yes, yes.
To that extent, we should do
yes.
it here.
So the first
Has any such study been made for all the dams, existing dams?
No. So the first thing is that there are many dams in many places. You take Himalaya, you take Northeast Himalaya, there are dams, very large dams in many places. Not all dams cause earthquakes. No, not all. You need a certain set, a combination of geological conditions that can trigger earthquakes in such scenarios. First thing you need is a basic fault of weakness, a geological fault, as they say, somewhere below. Okay. And then you need to know what are the stress orientations. Okay. Certain combinations of stress, the vertical stress and the horizontal stress, can actually trigger earthquakes. Other combinations, they will stabilize the crust. So they will act opposite. So really speaking, if I talk in geological terms, normal and strike slip faulting, geologists will know, the normal and strike slip faulting basically is one condition where you can have triggered earthquakes. Thrust faulting cases, you will not have triggered earthquakes unless the pore pressure, that is the pressure of fluids inside the rocks, is very, very high, very, very high. So otherwise you will not. Actually, they will actually stabilize the rock. So that is one geological condition. There are other geological conditions, the stress orientations and the fracture orientations, which I showed in one of the slides very quickly. So if they are favorably oriented, then you can have a good geological condition for earthquakes. So not all reservoirs trigger earthquakes. So coming to the second question, second part of your question, before any such big infrastructure projects are taken up, like dams, there are geotechnical investigations which are mandatorily carried out. Now, our goal is to learn from this exercise and inform what additional investigations we should do so that we know the hazard, potential hazard, much better in advance. So that kind of thing is our next step. First step is we have to understand how these earthquakes behave. And once we set up our deep borehole observatory, we will be able to know much more about that than today. And then the next step is hitting at your problem. Yes, I think it will be a very useful exercise.
Okay, I think it is a time to close. Sorry for.
I'm sorry I took so much. I spoke for so much time that
we have a platform to get the questions addressed. We have a big Google group which has got 6,500 members. And I appeal all the audience to become the member of Google group. Post your question. We will send the question and we will get it addressed. It's not a problem. So the second, I want to make an appeal to Dr. Sukanta Roy through this meeting. Some of our students may be interested to visit your laboratory, and the Science Forum can make an arrangement to facilitate the visit of laboratory. That's also possible. Is it possible?
Absolutely, absolutely possible. It is not very far.
Yeah, sure.
It is not very far.
Sure, we will be announcing in our Google group if we get a sufficient number, and we will find out a way to visit the laboratory. With this, now I would like to give it to Dr. Mr. Aditya to give the vote of thanks.
First of all, sir, you are saying that Earth is there for 4.6 billion years here, and it has got all the answers. Only thing is, you have to ask the right questions, and you need the tool. And you are rightly explained about the tool, and you have raised so many questions in the 100-odd brains. Please keep on asking those questions. You will get answer one time. With this, I give a profound thanks to Dr. Sukanta Roy for coming over here, and busy schedule. He finished the last meeting at 4 o'clock and rest to us. Thank you so much, sir. And this meeting would not have been possible without the support of ACL, that is Anna Centenary Library authorities. They consented to shift from 5th floor to this conference hall. Thank you so much for the Anna Centenary Library authorities. And how many of you have taken membership in this library? Please raise your hands. Recently, they have started lending books. So please make use of this excellent facility and be a member of. And students have got concession in fees, library fees and all. So please be a member. Subscription forms are available in the reception. And very simple formalities, you can be a member. And excellent collection of books is there. Please make use of this facility. And last, thank you so much all the participants for the patient hearing. Sorry that we are not able to give room for so many questions. Please raise this in the Google group. Thank you. Thank you all.
Those who have already registered with us for participating in this event, their name will be automatically added in the Google form today. And those who are going to give the feedback form, so you are going to fill up your email ID, those names will also be added in the Google form. Please do it. Within a couple of days, all of you, those who are interested, they will be added in the Google form. Those who are not interested, they can unsubscribe and get out of it. We will automatically add your name in the Google form.
Okay. So for those who are registered, one feedback, that QR code is there. If you are not able to, catch hold of that, it will be sent by email to you. Okay. So please submit the feedback and you will be getting the participation certificate. Okay, thank you.